Trojans Talk Research is a monthly spotlight on the research interests of Troy's faculty, presented by Troy University's Office of Sponsored Programs. This month features Dr. Raj Vinnakota discussing controlling light at the nanoscale, emerging frontiers in optoelectronics.
My name is Raj Vinnakota. I teach electronics courses, and I predominantly teach semiconductors, optics, and all that stuff. So I also serve as a director for Center for Materials and Manufacturing Sciences. So here's the title for my today's talk. So basically what we're going to talk about is like how to control the light at the nanoscale, right? You might have an obvious question, why we have to control the light at nanoscale, right? Why do we need that? So what I'm going to do, I'm going to slowly dive into the actual phenomena, why and what we need this nanoscale control for, right? So that's my device that we have already published the research article on. So before we dive into what is this nano control of light and all that high-level physics aspects, let's talk about a little bit related to the journey of light, right? So when I say the journey of light, I don't mean the history of light. So journey in understanding what is light, right? So the initial understanding of light has led to the classical optics, as you guys see here. In a bit, we're going to see what does this classical optics mean. And then slowly, as the curiosity improves, right? The scientists try to understand different aspects of light and how to use the light in various applications, right? So that led to quantum optics. We're going to see that too. Slowly, that curiosity increases, right? Because of the curiosity, right now we have AI, right, guys? So the same thing, applies to light as well, and its physics as well. So the quantum optics and its understanding led to the nanophotonics, and then it led to the plasmonics, which I'm going to go in detail and explain what each of this topic really means, okay? So this tells us, we are no longer just observing the light. We are actually controlling the light and also utilizing the light for various applications, let's say telecommunications, right? So what is this classical optics, right? Classical optics is pretty simple. So let's say, you have a reflector and then you just shine the light. So I don't know if you can see anything, but you see the reflection? So reflection, right? As simple as that. So we all know the light can be reflected. So that's one of the aspects of classical optics. So this reflection has led to many discoveries too, right? And also we have seen, like when we have a prism, right? And we shine a white light, the white light will be splitted into different colors, right? So until the prism experiment has done, nobody knows that white light actually embeds different colors of light, right? So that led to, understanding and curiosity. And again, this is all related to reflecting and refracting. But whenever we use a light can be absorbed too. And then it creates some energy, right? So when we talk about energy, so light propagates as an electromagnetic wave. So like a wave nature. And this embeds all the energy inside the light. Now, how we can understand light has an energy, right? So that led to the wave particle duality experimentation, right? What does this jargon mean, right? So as you guys see here, this is a source of light, and you have two openings, and light actually spreads, and each hole behaves like its own source of light, right? So can we demonstrate it? So we can really demonstrate that. So for example, I have the similar protrudings here. So this particular structure has like 1,000 lines per mm. So for example, if I pass through this, you see, the single laser pointer has now spread it into multiple points, you see. This is what this animation actually showing, you see. So can this happen at every length scale? The answer is no. So basically your your separations or the protrudings has to be very, very less. The size should be very, very less compared to the wavelength of your light. Okay? So that tells the light is propagating as a wave, right? So what about this dual nature, right? So can we detect the light? So that led to the curiosity of discovery of photons, right? So what does this photons mean, right? So now we understood the light can propagate as a wave, right? So now, can we detect it as a wave? Yes, but we need to understand the photonic nature of light, meaning like light actually has a particle nature too, right? So how do you understand that light has a particle nature? So I'll just take a solar cell. See, already solar cell, you can see the blue light is being turned on because of this light here. So if I put much more light, what happens is like if the light intensity is higher, and then you can see the blue light being glowing, right? I just used a solar cell, right? And then I just used some light source, but here is the red light source. And then I can see it's powering an LED, right? So how we can understand this aspect of light? This can be understood if and only if we treat the light as a particle nature. So this leads us to an understanding that light has a wave nature and also a particle nature. So that's where these two experiments come into very handy. So now, yes, we understood light can be reflected, refracted, it can travel as a wave, it has a particle nature. Good, right? Can we use it? That's the next curious question, right? Scientists always ask. So that led to the discovery of an optical fiber, right? What is an optical fiber? Basically, optical fiber guides the light, right? So and we usually hear about optical fibers, right? It uses for telecommunication or internet and all the stuff. So I have like an optical fiber here. Let's see if I can make it work. So if you guys carefully observe, you see, the light is coming out of an optical fiber. Now nothing is there, right? So what I'm trying to achieve here, I'm just using the light and trying to guide it, right? Almost you can visualize the guiding phenomena like you have a water reservoir. If you don't guide the water through pipes into your home, you don't get water to your home, right? We can't just go there and pick it up, right? The same thing, resulted in discovery of optical fiber. And this has revolutionized the entire communication industry because now the long distance communications can happen easily, right? So that's because the optical fiber can carry the signals for a longer distance without losing the actual signal, right? Now, the obvious question always happens like, okay, now we guided the light through an optical fiber, right? Now, can I reduce the size of an optical fiber, right? So now, the size of an optical fiber is obviously, we can see it, right? Around a couple of centimeters, right? So now, they try to reduce the size of the optical fiber, and now the size of optical fiber almost the size of the hair. I mean, I don't have it, but the size of the hair, you see. So if you still reduce the size of the optical fiber, what happens? It will become into nano regime or a micro regime, right? So now it will be highly difficult to guide the light through that nanometer sizes. So that's where the question comes. And the obvious question is, can we observe that, right? Now, we always see the skies, right? Sky is a blue color, right, guys? So why it is a blue color? It's because you have that particles in the air, and when the sunlight falls, these particles, instead of guiding the light, it reflects the light, or scatters. Let me rephrase it. It scatters the light. It's scattering because it cannot guide it or do anything of it, right? It scatters. So scattering happens whenever the feature size of the particle is much, much less than the wavelength of the light, you see. So that led to the discovery, or it opened the window for the science towards the nanophotonics. Basically, you can actually create a sub-wavelength structures and guide the light through it, you see. So that's another engineering marvel. So now, this led to another branch of science called plasmonics. So nanophotonics basically helps to understand how to guide the light, modulate the light, and all that different aspects. Now plasmonics actually deals with light interaction with electrons. So that's where the branch spreads into. So electrons, we already hear that word all the time, right? So when we take a metal has free electrons. Now, basically, when we shine the light on a piece of metal, what happens is the light intensity and the momentum, basically, it's been transferred to the surface electrons. And these surface electrons will oscillate. So these oscillations are powerful. And then, can we harness these oscillations? So that question led to the field of plasmonics. So now, this field actually have two divisions. One is called localized surface plasmon resonances. What does that mean? Let's say you have a particle, like gold, aluminum, or any metal particle. When you have a metal particle and when you shine the light on it, what happens, the metal has free electrons. So this electron cloud will now oscillate, right? So as you see in the animation there, it just oscillates. And when it oscillates, the word itself tells it's like a standing wave. It doesn't move anywhere. It just stays there, you see? So that oscillations are much more energetic compared to the light that is incident. Now this energy can be utilized in various applications. We're going to see that. So if we can harness that energy, if we can control that energy, we can have varieties of applications, right? So that's the field. And now, so the beauty about is like, it gets strong absorption and scattering at only specific wavelengths, not like every wavelength, you see. Let's say I take a gold particle and I use some white light, it will not happen. So it only happens at a specific wavelength of light, okay? And if we can harness that, we can have many applications. So the second division of plasmonics is called surface plasmon polaritons. So what are these? So we can visualize these as SPPs, which we call surface plasmon polaritons. We can visualize that as the surface waves that we observe in a still pond, right? So when we have a still pond or a still water, what we can see is just no waves or anything, right? Let's take a small pebble and just throw it on the surface. What happens? It disturbs the surface. When it disturbs, the disturbance is being transformed into the surface waves, right? And if you clearly observe, these waves will be in the surface only, not in the depth of your water. So the same phenomena can happen in engineering as well. So how we can happen that, or how we can do that experiment is like you need to have like a metal, like you take a metal and coat on the top with a dielectric, right? So if you have that particular layer, now you can shine the light, and then the junction between the dielectric and the metal will lead to generation of these plasmon waves. So these plasmon waves are no more like stationary, they are traveling too. Like how if you have string and then tap it, the wave has been traveling, right? Same thing happens at the interface now. So if we can harness that particular wave oscillations, what we can do, we can guide the energy in much nanometer or micrometer sized devices. So when we guide the light, we can also control the light, right? By again, discoveries, right? If we can control the light, now what we can do is like we can use that tiny waves as information carriers. So now we use electric current, right, as information carriers, right? In our electronic devices, we have microprocessors and microcontrollers where we use electric current to transfer the energy, right? or the data, whatever we call it as. So now, you can really reduce the size of that particular structure, and instead of using electric current, you can also use the plasmonic waves, right? But we are way ahead in discovering that particular aspect. Okay. So now let's take a step back and try to go and observe a little bit of history related to plasmonics, right? So plasmonics now we discovered, but it's been observed in the ancient history too. For example, let's say in the medieval stained glass, right? So you see different colors, right? Glasses are usually white, right, whenever the light passes. But now whenever light hits, the window now gives us different colors, right? Why it is giving different colors? So that's a question. So it's giving that colors because of that glass is now embedded with different plasmonic particles, or I can say like nanoparticles of gold, silver, or different material, right? That giving out those colors. At that time, yeah, it's fascinating, right? But now we are understanding why that color is being actually appearing, you see. Same thing, this is called like Lycoroscope. I hope I pronounced it right, So whenever the light falls on it, you observe a different color. Whenever the light transmits, you observe a different color, you see. So at that time, we just think it's a magic. But now we are trying to understand why that's happening, you see. So what I want to emphasize here is the plasmonic effects were already observed, but we are now understanding the actual phenomena, why that's been taken place. So now let's go back to our topic, and let's see how and where these applications of localized plasmon excitations can be used. So one of the applications is like sensing. So for sensing now, these nanoparticles are very, very tiny. So if you have a tiny bit of material, you can sense that material now. So you don't need like a couple of milligrams or milliliters. It's very, very tiny is needed to observe or sense something in that material. Same thing, for example, in imaging too. So in MRI and everything, now the direction is like to improve the clarity of observation, right? How you can do that? Now you can insert these particles into a space where you want to observe that particular image. So this image now will be enhanced, and you can get much more localized observation. Almost like this. You have a 2K resolution, 4K resolution, 8K resolution TVs, right? Same thing can happen in the MRI too, you see? And the other applications is like solar cells. We've been using solar cells, right? But the efficiency of solar cells is very, very limited. So it's not 100%. It is around 20 to 30%, you see? Even 30% to get is like very rare. So to improve the solar cell efficiency, one way forward is like using plasmonics. So you can use these particles, and as we observed in the previous slides, we can harness the energy that has been absorbed or squeezed by these particles. And that energy now creates a different channel to increase the amount of power generation from the solar light. So that way of research is also one of the budding areas. And also another biomedical application that Rice University is doing is related to, and a couple of other universities too, it's related to photothermal cancer therapy, you see. So if you have a cancerous tissue, you can actually inject these particles, and these particles just lay around this cancerous tissue. Now you can use the light and cure that particular tissue, you see. So the advancements are like going on. So what about the surface plasmon polaritons, the second division? So as we already seen, this particular phenomena can help to squeeze the light into sub, wavelength dimensions of the device, okay? So basically that's called like a diffraction limit. So in science, the word is diffraction limit, meaning like you cannot channel the light on a structure that has the size less than the wavelength of the light, almost like lambda by 2 it should be. So now this particular phenomena can help us to guide the waves, right? So now we can see like the actual propagation in an animation. So these are the propagating waves. So this is a simulation done. So, you know, simulations are very, very good tools to understand this nano phenomena, right? Experimentation is an observation, but simulation helps to deeper diving. So this is a simulation of showing like how these waves have been traveled, right? Now the obvious question is how to excite these, right? So how to excite these waves? So the excitation can only happen if you have some kind of gratings, right? So these gratings basically help to match the momentum of these surface waves and then the free space wavelength, okay? So, you know, how we can understand now the light is being squeezed or not is by relying on the analytical formulations now. So here it is, we have drawn the frequency versus the wave vector of the light and the wave vector of the surface plasmon polaritons. As you observe, this is the wave vector of the light, and then at a certain frequency called the surface plasmon polariton frequency, the wave vector of the SPPs are much, much higher, as you guys see. It's like very higher. So this tells basically the light is squeezed. So, and this helps us to understand we can actually guide the light in nanostructures, okay? And this is called dispersion relation. So now, basically, what is the need for all this nanoscale light control and all that, you know, high-level engineering of optics, right? So one way or one application to look at is, let's say we see the microprocessors and clock speed and transistor count on a microprocessor. Okay, so this is the historical trend of Intel microprocessors transistor count. So as we observe, so the green dots are the clock speed of a transistor and microprocessor, and then you know the red dots or the orange is like the transistor count on a microprocessor. So we see that the transistor count is being increased, right? So that's called Moore's law. But what about the speed? The speed is now not linearly increasing. It's been reaching a plateau, so almost 3 gigahertz, right? So for example, when we buy laptops or something, we can see what is the speed, 3 gigahertz, and now turbo speed is 4 gigahertz, right? So that's limited. It's not been increased like the way we expect it to. So the reason behind that is not the transistor speed. The transistor speed can be improved, but now you know, we have to transmit the data between 2 chips or 3 chips, right? So when we're transmitting the data, we are using metal and then electric current. So this is slower. This is not as fast as we think. So that, though the miniaturization of transistors happen due to the current semiconductor fabrication technologies, but still, because of the interconnect delay times, the saturation in the speed is being observed, right? So what we can do to surpass this particular limitation, right? So one way is like we can use optical fibers, right? So to, instead of the actual interconnects, like metal-based interconnects. Yes, we can use that, but now the size of the transistor or the microprocessor, I mean, all the transistors are embedded in the microprocessor. How much is that? It's been nanometers, micrometers, right? So that's like much smaller sizes compared to the optical fibers. So now, if the size is very, very less, we can't use just optical fibers, because now we are entering into a regime of diffraction limit. In order to tackle that diffraction limit, and in order to understand how we can match the feature size of semiconductor electronics with the optics, right? So the plasmonics field basically provides an opportunity to create newer and novel devices, right? It's not yet implemented, but it can give the actual opportunity to find different solutions. So the advantage is you still get the similar speeds comparable to the photonics or light-based speeds. And another second advantage, they can be very small in size. So that is the advantage of this field of plasmonics. So many researchers and professors and different universities have done various devices how to control this plasmonic energy, right? So here are different devices that have been already published. So here they have like a metal dielectric metal, and then they have a light that's been passed. Using the electrical energy, now they modify the modulation of the light that has been traveling. Similarly, they have a silicon-based device, and there is a device on using losses, okay? So at the end of the day, we need to have on and off states, right? Because the information is always ones and zeros. Though we talk, the actual information that the microprocessor can understand to process is ones and zeros. So that's what we need to get it. Turn it on, turn it off, that's all. So now all these devices basically use the metal dielectric structures. So if you carefully observe, I mentioned when we use a metal, we can use only certain frequencies or one frequency. So there is no tunability of operation. So it only gives us like one. Let's say we bought a laptop and we can't install anything. There's no tunability. Same thing, there's no tunability. So to get the tunability, so we have to rely on semiconductor rather than just a metal. So that's where we are transitioning our presentation into. And the another thing that we need to observe here is the fabrication as well, right? If we have to fabricate these devices, we have to use a different fabrication techniques. But right now we already have semiconductors, and we have like very great techniques and fabrication facilities. If we can suggest a device that can use the existing fabrication techniques, that's a beauty, right? So that's where we are heading into. So this particular plot tells us like why we need that importance of semiconductor plasmonics. So the metal-based plasmonics have a lot of speed that they can offer. But can they match or integrate it into the semiconductor electronics? Basically very difficult, because there's a gap here, you see? So that's very difficult. So because the clock speed at which the semiconductor electronics working is different, the feature size is different. But let's say the semiconductor plasmonics, they can match the feature size, and also they can give larger characteristic frequency of operation. So now in my research group, so we have suggested few devices. So these are the 3 varieties of devices we have already suggested, and it has been published too. So one of the device is like using N-type and P-type sandwich, which we call a diode. So when we have an N-type semiconductor sandwiched to a P-type semiconductor, it forms a diode. And what is a diode? Diode is an electronic switch, as simple as that. Okay? So can we use this electronic switch and suggest a plasmonic diode or a plasmonic switch? That's a question. So here what we do is like we have the gratings to couple the input signal to the surface plasmon polaritons at the interface. So we can couple that. And now, can we switch them? That's a question, right? How to switch them? We just give electric voltage. Now that electric voltage results in injecting more electrons from the N-type layer into the P-type layer. So that electrons, when they go into this P-type layer, or I say this an active region, usually that's the wording they use, that active region will result in modification of the material parameters. So when that modification happens, the SPPs will turn off, because that interface will no more be dielectric metal interface. It is the metal-metal interface, you see. So here is another structure. So this is, we suggested in a simulation fashion. Numerically, we have a proof of concept. So this particular structure, we actually fabricated with a collaboration with UT Austin. So this is an actual fabricated structure. And then the proof of concept has already been, suggested that during the fabrication as well, experimentally we have proved it. So, and the another version of a diode, like a PN diode, is called a metal semiconductor diode. So that's called a Schottky contact diode. So we have used now the Schottky contact instead of semiconductor contacts or junctions. So even if you use a metal and a semiconductor, you still get a contact here, a junction. So this particular diode structure also works in the similar fashion. Whenever you put light, the electron starts moving. And this movement will result in changing the active region's material parameters, and that gives switching. Now the obvious question is why two varieties, right? Two varieties are because different output results, okay, which we're going to see in the future slides. So one is faster than the other. So this slide basically helps in detail to understand how the device works. So, this particular junction helps the excitation of the surface plasmon polaritons. And then now, under the impression of voltage, the carriers move in the active region. So carriers are nothing but electrons and holes, right, that we have. So when they move, what happens, like, I know we are talking little technical wordings, but the space, this active region space, its permittivity gets modified. When its permittivity gets modified and it moves towards the metallic permittivity, that's when we observe the switching, because it's no more a different junction, it's same material. Also, whenever there's a flow of electrons, there's a resistive losses too. A heat will be coming out as well. So this particular movement of electrons will result in heat dissipation as well. So initially, how we have perceived the understanding of this device is by relying on numerical strategies. So we have different tools, but we have relied on COMSOL multiphysics, and because the entirety of understanding the device, output characteristics is by understanding how this semiconductor electrons and carrier transport happens under the impression of external voltage. At the same time, when the electrons are moving, we know the heat is generated. So we need to calculate that heat as well. At the same time, the SPPs are electromagnetic waves, so we need to solve the Maxwell equations. So it is a complex phenomena. Now we have to solve the integrated approach, Maxwell's heat and semiconductor equations together to understand the actuality of the device working principle. So now once we have done the simulations and everything, so here is some calculations that tell us at what particular voltage you will understand or observe the switching of these SPPs. So here, when we give 0 volts, we can see this SPP is traveling. And now when we increase the voltage, we see some modulation takes place and switching happens. And we can also observe the change in temperature locally. This is a scale that observes. At the same time, the electrons are moving, right? We need to observe that electrons are moving or not. So we can see the shift in the electron density. So here the plots tell us like how this switching happens. This is a transmittance plot that tells you like the SPPs are switching at this critical voltage. So this direct transition into 0. So this is 1, this is 0. Okay. And then we can also observe that in the diffraction, I mean, the NSPP, I mean like the refractive index versus the frequency plot. Okay. So that's called the dispersion plot. So again, so this is like when we use both semiconductors, so we still observe the same modulation. But if you carefully observe, the responsivities is minus 500 dB per volt, and the modulation is minus 100 dB for semiconductor-semiconductor contact. However, if we see the metal semiconductor contact, we got like minus 100 dB per volt. So there's a difference there, you see. So now how you can couple those SPPs, right? So we have done the simulations too. So now we used two fibers. So one fiber basically helps to launch the waves, and that waves now travel as a surface plasma polaritons. And now to capture the waves in the other side of the device, we still have those gratings, and the gratings will help convert the SPPs back to light. Okay, so these are the experimental implementations. So this slide basically helps us to understand how we fabricated. So we haven't fabricated here. So we fabricated in UT Austin. So UT Austin has done all these fabrication aspects. So this tells us the entire flow of fabrication, and these two tells us how we have launched the SPPs and then detected the modulation of SPPs under the impression of electrical voltage, you see. And this is the doping concentrations we have used. So now whenever we design a switch, we need to understand whether it can have a repeatable on and off switching. So one way to do is like now you can on and off the input signal, right? At the same time, now you can on and off the voltage. So once you on and off the voltage, so on and off, you should observe the same change happening in the signal as well. So this is like a step response for PN diode based, and the step response for a Schottky based switch. So it tells like the off time is 400 picosecond, on time is or rather this is on time and this is on time and this is off time. So same, if we observe the Schottky, 800 picosecond is the on time, 500 is the off time. Okay, and different plots are because different doping. So this is what I was talking about, tunability. So we can actually tune the operational frequency and everything by changing the doping concentration. So tunability is like this. We have a water. Now if you want to have a salt water, just put a salt, you'll get a salt water. That's the tunability of water. If you want a sugar water, just take a pure water and add sugar, right? That's a tunability. So that's what the doping does here too. So here we have done the calculations of on and off switching as well. So as you see, for different doping, the switching of off time and on times changes. So let's say for ND 110 power 24, we got around 100 picoseconds as the off time, and then on time is around like, what is it, between 10 to 20 picoseconds, you see. So that means around 120 picoseconds is a switching time on and off. The same thing we have done for the PN diode based analysis. So here is the entire comparison that tells you like the difference between the two devices. So here we have done silicon based and indium gallium arsenide based device, the same structure, two materials. So we observed the signal modulation of minus 100 dB. When we compare that modulation with Schottky, it's like minus 20 dB. So whereas the responsivity, meaning like how much modulation we observe with the change in voltage. So for PN diode based device, silicon is minus 1000 dB per volt, and indium gallium arsenide minus 500. Whereas Schottky is giving much better response, minus 1800. So that's where we have to choose which one is required for a specific application. And then the times. So the on and off times for silicon is like 100 picoseconds, whereas indium gallium arsenide 20. So if you want the fastness, we have to use indium. And then for Schottky, we observe 125 picoseconds. Of course, these are simulation based, so when we do experimentation, the other aspects will fall into place, and these times will change for sure, But this is a proof of concept. So the 3 dB bandwidth also we observe, so 40 megahertz for the PN based, but we push the limit to 4 gigahertz for Schottky based diode. Also, we need to understand whether our basic fundamental device can be used to generate and or logic gates, because logic gates are basically the next building blocks for the microprocessors or microcontrollers. So we have used our waveguide. So wave is guiding, so it's a waveguide. So plasmonic waveguide, and we have structured into Y shape. So when we do the Y shape and give voltages on the Y structure, by modifying the V to be higher, or V1 to be the higher, or V2 to be the higher, right? So we can play with V1 and V2 voltages, and you can get the entire truth table of on and off of the logic gates. So here, the simulation result shows you let's say when both the voltages on the Y structure are off, less than the critical voltage, you see the data has been transferred freely. Now, if one of the voltage is higher, you can see it's only flowing from one channel, right? Similarly, the other aspect. So this is the NAND gate and NOR gate truth tables, and the truth table aspect can be understood by passing the signals at either of the waveguides and observing the output signal. You see? So yeah, that's it for today. So I have a collaborator from Louisiana Tech and also UT Austin, and the project is also supported by NSF. So we have NSF funds. So I try to reduce the physics aspect, so it will be good for the crowd. Any questions? Yeah.
I have a question about the fabrication. Can you tell us the technique that you use for fabrication and the dimensions of those?
Yeah. So as you see there, so we have a sample that has a P and N doping. So usually fabrication, how it happens, take one semiconductor sample, like say silicon, and now you inject with holes, so it will be P-type, and then using the gases. And now you inject with electrons. So now you form the NNP layer. And if you observe here, depending on the temperature that you use and the amount of time you expose those gases, you can form the thickness. So here the thickness of the N layer is 1 micrometer, and the P layer is 750. 750 nanometer. And now you flip the device and you evaporate the gold on it, so you get a gold contact there. So now once you're done with that, you need to form these particular grating structures. So what we need to use a mask. So this is a mask here, and now you etch this part of unexposed area. So the red area that you see is a mask. So the
lithography, something like that?
What is it?
Is it like lithography?
Yeah, lithography, exactly, you're right. So they use lithography to do, or etching based method too we can use. So etching is a wet, lithography is a non-wet. So you can trench here, and then now you can again form silicon nitride here, and then you can form the gold, and then you can use wet etching to form the gratings, and then using those gratings you can launch the waves. So this is the SEM image on the side of the device that can, or it's rather on the side, yeah. So this side of the device. So now you can understand the P-type, see, N-type, and if you carefully observe, you can also understand the interface. So, and these are the actual grating structures. So, yeah, sure.
Trojans Talk Research is a monthly spotlight on the research interests of choice faculty presented by Troy University's Office of Sponsored Programs.